Okay, so in this problem, you're told that an evacuated reaction vessel is filled with 0.8 atmospheres of nitrogen, 1.68 atmospheres of bromine. When equilibrium is established, according to the reaction below, there are 1.42 atmospheres of bromine remaining in the vessel. And then you're asked for the equilibrium constant, the K sub P, for the reaction. And here is the reaction that's going on. Okay, so this is another type of Rice table problem. You can either be asked to solve for equilibrium concentrations of different things in a reversible reaction, or, as we have in this case, you are asked to figure out what the equilibrium constant is. And you do that with a Rice table. Okay, so we know that a Rice table has these four rows. It's got the reaction, it's got the initial conditions, the initial amounts, the change in the amounts, and then the equilibrium amounts. So we'll make our rows, and then everybody in the reaction gets their own column. So we've got the NBR3, and that reacts to form the 2, and that reacts to form an N2 and a 3 bromines. Okay, so make those our columns. All right, and look at what we're told to start filling in some of the blanks here. And we're told that we have 0.8 atmospheres of the nitrogen, and we're told that we have 0.168 atmospheres of bromine. And again, because nothing is said about the nitrogen tribromide, what we know is that means there's zero amount of that. And so initially we pump some of this in, and nature doesn't really like that because nature wants there to be some of everything. That's the nature of these equilibrium chemical reactions. And also, if you think about it in terms of Q, right now Q would be much, much bigger than the equilibrium constant. Whatever it is, we don't know what it is, we're going to calculate what it is, but we know that nature is not happy with all product and no reactant. So the reaction is going to go in that direction. Okay, so that means in terms of nitrogen, we're going to lose X amount of it. And for every one of these nitrogens that I lose 3 bromines. So we're going to lose 3X amount of the bromine. And I know that for every nitrogen and 3 bromines that I react, I form 2 nitrogen tribromides. So that's going to be a plus 2X on that side. And then we know that with the row for the equilibrium amounts, we just add up these columns. And so this one is just going to be 2X. This one is going to be 0.80 minus X. And this one is going to be 1.68 minus 3X. Okay. Well, we're also told that we know that after we have let it establish equilibrium, there's 1.42 atmospheres of the bromine remaining. And that's important because then we can figure out what X is. We're going to solve for X right there. And if you do that, I'll let you do the algebra, but you can figure out that X is equal to 0.0867. Okay? And so now, what that means is, I can just go ahead and plug that in. So 0.80 minus 0.0867. So that's going to be equal to 0.713. Okay? And then I could do 2 times 0.0867, and that's going to be my equilibrium concentration of the nitrogen tribromide. And so that comes out to be 0.173. Okay? So, because I was able to figure out X from the bromine, now I know the equilibrium concentrations, or the equilibrium amounts of all 3 of the compounds involved in this reversible reaction. And so now I just will end up plugging those into my expression for the equilibrium constant. Okay, and I know how to develop the expression for the equilibrium constant. It's just going to be the products over the reactants, and so this will be a partial pressure of the nitrogen raised to the power of its coefficient, so that's just going to be a 1. The partial pressure of the bromine, Br2, raised to the power of its coefficient, so that's going to be cubed. And we divide that by the partial pressure of the nitrogen tribromide raised to the power of its coefficient, which is a 2. And so I can just substitute in the numbers now. The nitrogen I have is 0.713 times for the bromine, so that's, 1.42 quantity cubed. Okay, pardon that. right there. And then for the nitrogen tribromide, that's 0.173 quantity squared. Okay? So if you do the math for that, you get 68.2 is the equilibrium constant for this reaction. And it is unitless. Remember, this just represents a ratio of products to reactants, so it has no units.